Donc, merci à vous tous d'être venus si nombreux. Je vais laisser parler avant moi Monsieur Vincent Paillard, vice-président en charge de la CFVU de l'Université. Et après, moi, je vais dire quelques mots avant de vous laisser avec notre conférencière Jocelyn Bell.
Ok. So, welcome to Toulouse, Professor Bell. I'm going to switch to French to give a few words. Ok. Bon, donc, je représente la présidente de l'Université de Toulouse, qui ne pouvait pas être là aujourd'hui. Bon, c'est un grand honneur d'accueillir le professeur Bell, qui a accepté de donner son nom au télescope 100% étudiant de l'Université de Toulouse, qui j'espère aura un grand succès, en tout cas autant que l'affluence que je vois ici. Il y aura beaucoup de gens pour s'en occuper et pour faire des belles choses. Donc on est très heureux que le nom de Jocelyn Bell ait été choisi et qu'elle ait accepté aussi de donner son nom, parce que bon, non seulement elle a une très grande valeur scientifique, une très grande carrière dans le domaine de l'astrophysique, elle a eu un très grand nombre de prix, mais aussi bon, c'est quelqu'un qui a des qualités humaines, donc qui a par exemple eu un prix et a donné l'intégralité de son prix à une fondation à l'Université d'Oxford pour aider des étudiants qui n'auraient peut-être pas pu faire des études dans ces conditions. Et donc, ça rentre en résonance avec un certain nombre de critères de l'Université de Toulouse qu'on veut aussi mettre en avant. Donc, nous, on a un prix beaucoup plus modeste des étudiantes inspirantes, donc, par exemple, pour augmenter la place des filles dans les matières scientifiques. Et donc, c'est pour nous quelque chose qu'on veut mettre en parallèle. Donc, cette carrière non seulement de grande valeur scientifique, mais aussi de qualité humaine, c'est ça qu'on veut mettre à l'honneur ce soir. Et c'est pour ça qu'on est très heureux que ce nom ait été choisi et que le professeur Bell ait accepté de donner son nom et d'être là ce soir pour vous présenter ses travaux. Et je vais laisser la parole maintenant. Je vous remercier d'être présents, déjà très, très nombreux, et laisser la parole à la présentation de UPS in Space, avant de laisser la parole au professeur Bell pour sa conférence.
I will start in French for the audience, and after I will speak in English for you. Donc, merci à vous tous d'être présents ce soir dans le cadre des journées portes ouvertes de l'Observatoire Jocelyn Bell de Toulouse, qui font suite à l'inauguration que nous avons eue en décembre dernier. Et ce qui nous tenait à cœur, c'était aussi de faire parler notre marraine, donc le professeur Bell, qui depuis très longtemps s'engage aussi pour la vie étudiante et les vies de campus et je fais que rajouter des « et », mais aussi pour la place des femmes dans l'astro, en général, de la place des femmes aussi dans les sciences. Très rapidement, nous, c'est aussi la fin de la partie projet de l'Observatoire Jocelyn Bell de Toulouse. Notre observatoire est fonctionnel, marche. Si vous avez pu voir au fur et à mesure des différentes présentations d'aujourd'hui, pour ceux qui sont venus, les premières images, les premières lumières de l'observatoire. Il est clair que cet observatoire, nous l'avons voulu pour les étudiants qui sont présents dans la salle. C'est un observatoire qui est le premier observatoire 100% étudiant, géré, créé par des étudiants ou des anciens étudiants, vu que c'est un projet qui dure depuis plus de 10 ans. Ceux dont ça rappelle quelque chose, je vous vois là. Et c'était juste pour vous dire ça, donc bienvenue à l'Université de Toulouse. Et thank you very much, Professor Bell, to come to visit us here in Toulouse, in the south of France, so far away from your original land of Oxford. It's a pleasure, and we will, in the name of all the members of UPS in Space, I will thank you a lot for accepting to give your name to the observatory, and it's a pleasure to have you here for this lecture. So it's your turn to speak, and after I will close with some closing world. Thank you very much.
Thank you. Thank you for the kind introductions. I am going to have to speak in English, but it is Scottish English, which is superb English. So, we are made of star stuff. Really? Is that true? I'm going to have to talk a bit about the chemical elements. I will talk about the Big Bang that created our universe. I will talk about how stars create some of the elements, and about star death, which creates many more chemical elements. And then I'll talk finally a little bit about how those elements came from the stars to be in planets and in people. So first, a little chemistry, just a little. This is a student answer to an exam question. I hope your English is good enough. This is a rather longer one. Gin is a drink. Yes, okay. It would never happen in Britain, of course. So I'm going to have to talk about a number of different chemical elements. You're probably familiar with this table, maybe not with this color scheme, but at least with the pattern, the layout, and how it starts with the lightest element, hydrogen. You read across like lines in a book. So the next element you come to is helium. Oops, that's not what I meant to do. Laser, which doesn't really work on the slides. Okay. So hydrogen, the lightest element, read across like the lines in a book. The next chemical element we come to is helium. And then we jump back and down a line, and it's lithium and beryllium, and read across to neon, and jump down a line and come back to the left-hand side, and so on. And this is a list of just about all the known chemical elements, certainly the stable ones. We might yet invent or create some more unstable ones, but this will do for now. But there's about 200 chemical elements in that table, and you don't want to be here hearing me discuss all of them tonight. So we'll focus on the chemical elements that are in our bodies. So here is a question for the audience. There's a lot of water in our bodies. What chemical elements are in water? Hydrogen, oxygen. Good, we've got two. We are organic things. Carbon, right. What makes our blood red? Iron, yes. There's lots and lots more chemical elements. Those are probably the most prominent ones. The other ones are important for things like our mental health. They're not there in large quantities. They're not very common elements in our body, but they're necessary. So we've got hydrogen and oxygen, which we mentioned in the context of water, carbon, calcium in our bones, iron making our blood red, and small amounts of many other things, including especially sodium, potassium, lithium. I'm going to concentrate on the first 5, so down to here. And if we can understand how those elements came into existence and came to be in our bodies, then we'll understand most of the story. Now, when we were born, we were this sort of size. We're bigger now. There are more atoms, more molecules in our bodies. Where have those molecules come from? Any suggestions? Food? Good. We also breathe, but we breathe in and breathe out. Slightly different elements breathing in from breathing out. Oxygen stays in our bodies. But most of the chemical elements have come from our food, and we know that if we have too many, there are consequences. So then the question is, where did those atoms come from? They came from our food. Where did the food come from? Some of it's animal, some of it's plants. The animals largely eat the plants, so if we can understand where the elements in the plants came from, we'll understand the animals and us. So botany is okay as a subject, it's important. So plants start as tiny seeds with very few atoms or molecules in the seeds. But they grow, they get more atoms. Where are those extra atoms coming from? The earth, indeed. Maybe some from the air, but you have to be careful. Some of the things are exchanged rather than stay with the growing plant. So it's primarily the earth. And where did the atoms in the earth come from? So we're into the origins of the solar system. And where did the atoms that the solar system was made from come from? And where did those atoms come from? And so on. You can keep, as a lecturer, being troublesome, asking questions like that. I think it's simpler if I start at the beginning and work forward, same direction as the arrow of time. So I'm going to talk a little bit about the origins of the universe and end up talking about us. So it's a lot, and it's already quite late. Our understanding of the universe is that it began 13.7 billion years ago, and I'm using billion in the scientific sense, 1,000 million, 10 to the power 9. The press sometimes uses billion in a more flexible way. And it does genuinely seem that before that big bang that created the universe, we can't get information about that, but working back as far as we can, it seems that everything was compressed in a tiny volume. Everything was energy as well as matter. So energy is the potential to do things. And everything did not like being squashed in a tiny volume and went whoosh. And this is officially called the Big Bang. This is the proper scientific name, really, honestly, for the explosion that created the universe 13.7 thousand million years ago. And what started as a tiny, tiny bundle of energy, I suppose, expanded. And it is still expanding today. We can see the galaxies moving further apart today. It's still going on. And it's from tracking the expansion today that we worked out that it was 13.7 billion years ago. Now, an explosion of everything from a tiny volume is clearly a big explosion. And it's very hot, but it's expanding. Maybe some of you have bicycles or cars. If the air comes out through the valve from the bicycle or car tire, it's quite cold. Have you noticed? So air expanding suddenly is cold because the expansion takes away some of the temperature. The initial universe was very, very hot, but as the universe expanded, it too cooled. The temperature came down and down. Initially, it's very bright. It's blinding. Your sunglasses would not be good enough. You would be blinded. It's very, very bright. But as it expands again, it cools, and the light diminishes. It gets fainter. And some solid stuff starts to form. It's using Einstein's famous equation, E equals mc squared. Some of the energy from the expansion and from the radiation turns into mass, matter, solid stuff. This is the first solid stuff, created shortly after the Big Bang, and increasingly so as the Big Bang cools with expansion. So after a few minutes, the temperature of the Big Bang is down to 1 billion Kelvin. And I'm using billion in the scientific sense, 1,000 million. And when it gets down to about 1 billion, you start to get the nuclei of very simple atoms created, like the hydrogen atom, which is not complicated. Its nucleus is a proton. But also helium, which has protons and neutrons, and heavy hydrogen, which has some neutrons as well as the one proton. So a few minutes after the Big Bang, some solid stuff has been created. So on our periodic table, we've got some hydrogen on this side and some helium up top on that side, but nothing else. So no carbon, no oxygen, no us. We couldn't exist. We come much later. Now, in Britain, we have a children's story called Goldilocks and the Three Bears. Is it known here? Excellent. Okay. In this story, it's for, children this age, a little girl with golden hair is out on her own one morning. Why? Where are her parents? What's going on? She is out on her own one morning, and on her walk, she finds a house that belongs to 3 bears. Daddy bear, mummy bear, baby bear. Daddy bear, mummy bear, and baby bear are out for an early morning walk. The house is empty. She goes in. Do you have a story like this here? Ah, you know the story. Good, right, okay. So she goes in and she tries the dishes on the table, the porridge. Daddy bear's is too hot, mummy bear's something wrong, baby bear's is just right. So she has baby bear's porridge. She tries their chairs, something wrong with daddy bear's, something wrong with mother bear's. Baby bear's chair is just right. She tries the beds. Something wrong with daddy bear's bed, something wrong with mummy bear's bed. Baby bear's bed is just right. And if I remember, she falls asleep on baby bear's bed, which is a very stupid thing to do. But this idea of things being just right, some things being just right, has been taken over into science in the English language, and we call it the Goldilocks effect, when conditions are just right for something to happen. And in the very early universe, which we have here on this timeline, Big Bang is somewhere off there. This is 1 second after the Big Bang, 3 minutes after the Big Bang, and today is somewhere long way over there. And in the early universe, just after this Big Bang, it's very hot, it's very dense. Any particles that there are going at great speed because of the high temperature, and they collide and they break up, and it's a bit chaotic, and nothing of use happens because everything is frantically running around and banging in and colliding. After 1 second, the temperature is cooled quite a lot, and from 1 second till 3 minutes after the Big Bang, some of the particles that form can survive, just some. So we have protons, or alternatively known as the nuclei of hydrogen atoms, single protons. And shortly after that, some neutrons get formed and we get the nuclei of helium atoms, or alpha particles. Some of you may know them as. And that goes on for about 3 minutes. But all the time the universe is expanding and cooling. Think of the air coming out of that bicycle tire valve. As it expands, it cools. And 3 minutes after the Big Bang, the thing has expanded so much and got so cold that no more things can be created. We have made some nuclei of hydrogen, or protons, and we've made some nuclei of helium, but nothing else can be created. So how were we and our world and animals and everything else created? Because with the expansion, the chances of building something bigger are very, very small. But we are here, we do exist, and so do the cows and the horses and the cats and all the rest of it. But in terms of what we need for life, the universe has not yet given us that. Certainly in a bad way, not yet given us that. I said there was hydrogen and helium. If I'm being strictly accurate, there was probably also some lithium nuclei and some beryllium nuclei, but they were probably unstable nuclei. So they did spontaneous radioactive decay and went back to being protons or neutrons or whatever. And we're not making any more chemical elements because the universe is expanding and expanding and expanding and cooling and cooling and cooling. It's a one-way street, as they sometimes say in America. But we know that there are other chemical elements. We know there are in us and in our world. So where did they come from, if not from the creation of the universe? And the quick answer, if you want to go to sleep, is stars. Stars made the other chemical elements. And I'll tell you a little bit about that and how those chemical elements got from the stars to us. So we've got probably some gas dust particles milling around. They're very chemically very simple to begin with, but they mill around, and by chance there'll be a knot with slightly higher density, slightly higher gravity, which will pull in 1 or 2 more particles, which will put up the mass of this central bit, which will put up its gravity, which will pull in some more particles, which will put up its gravity, which will pull in more particles. And over a very long time, maybe millions of years, this accretion, this pulling in particles, makes the mass bigger and bigger and bigger. And as it gets bigger, its gravity gets bigger, so it pulls in more, which puts up its gravity, so it pulls in more, which puts up its gravity, etc. And they tend to grow without fail. So lots of interesting things going on in this slide. It's part of the Orion constellation, one of the prominent constellations in winter in the Northern Hemisphere. And in part of the Orion sword is this nebula known as the Orion Nebula. And it has a lot going on. First of all, there are some big stars. And do you see that the stars have a nice cross shape through them? Christmas is coming. You will get a Christmas card, or 2 or 3, with a star with a cross through it. And maybe the 3 wise men, the shepherds who saw the star, and maybe their animals. It is strictly an anachronism. That cross shape comes from the telescope, and only from the telescope. It comes from the telescope because inside the barrel of the telescope there are mirrors that are held in place with 4 pins. And those 4 pins create the cross shape around the star. It's not there normally, and they did not have telescopes at the time of the 3 wise men and the birth of Christ. So your Christmas card showing the nice cross, okay, good theology, bad physics. So that's stars, okay. This red material is hydrogen. Hydrogen has a spectral line in the red. It's a prominent one, and in many astronomical photographs you'll see large patches of red. And every time you see a large patch you can say, ha, hydrogen. And you'll be right every time. So you want to impress people, hydrogen. It's the commonest element in the universe as well, so it's a fairly easy win, that one. This particular one is known as the horse's head because of this shape. Perhaps I don't need to say it's not really a horse's head, but okay. But this slide is also of interest to us because the horse's head is part of a dark area, which has probably got quite a lot of dust and maybe quite a lot of interesting, useful chemicals in it. And it's in dark patches like this that stars begin to form. By chance, there's a group of particles close together. Extra gravity pulls in more particles, puts up the gravity, pulls up. You've heard all this before. As it gets really big, the temperature in the center of this growing ball gets quite hot. And when it reaches some millions of degrees, nuclear reactions can start. And the nuclear reactions release energy, and the star can start to shine. So if you have any relatives who are anxious about nuclear reactors, I do, maybe you do, you can say, well, the sun is a nuclear reactor. And if we did not have nuclear reactors in the sun, we would have no sunshine, no life on Earth. They are a necessary part of life, but the art is to control them or have them 93 million miles away in the sun. So this slide shows that there's quite a lot of hydrogen kicking around, and that hydrogen is what starts stars. So we get stars shining. I think the main message on this is we're talking quite large temperatures. A star that's shining has a temperature of about 10 million Kelvin in its center. And it's doing this nuclear reaction, hydrogen converting to energy. Now, ultimately, of course, it'll begin to run a little short of hydrogen. But for a typical star like the Sun, and the Sun is a very average star, enough hydrogen to keep the star shining by this nuclear reaction for about 10 million years. And we're only about 3 million years into it, so you're okay. You can live in comfort. But ultimately, this process will stop because all the hydrogen's been used up and converted to helium. Nature has another trick to keep the star shining, and that is to merge helium atoms, 3 helium atoms merging in a nuclear reaction to create a carbon nucleus. And this is the first mention of carbon in our universe, an element that's very important for us and for life. So to do this in a different way, the first kind of star that I talked about, the initial stars, they're converting hydrogen to helium in their centers, and outside that there'll be hydrogen that is not yet converted or won't be converted. The outside of the star is hydrogen nearly always. The next stage involves bigger stars, and that's when hydrogen untouched, hydrogen converting to helium, as in the old process, and now a new process, helium converting to carbon. 3 helium nuclei merging in a fusion reaction to create carbon nuclei. And this is the first mention of carbon in the universe, and it's important for us. We're a form of carbon-based life. So the elements we need for human life, we've got hydrogen, we've got carbon, we don't have oxygen, we don't have calcium, we don't have iron, we don't have potassium. What's the universe going to do about that? Do you mind telling us? Sun's life will end with the conversion of hydrogen to helium. It will swell and become what we call a red giant star. It will swell, engulf the planet Mercury. It will swell and engulf the planet Venus. Whether it engulfs planet Earth or not, it's a bit hard to tell, but if a temperature at some millions of degrees comes this close, I'm not staying. So Earth will, if not engulf, at least be seriously burnt. Sun's life will end at that stage. Having done this swelling and engulfing, it shrinks back to be a dwarf star, quite small. But fortunately for us, for life, there are also stars that are much bigger than our sun. For instance, Betelgeuse in the constellation of Orion, some of you may know, or the Pleiades, a group of stars not very far from Orion. They're all much more massive stars, and more massive stars can do further nuclear reactions. So the first thing that happens is we had carbon. That's where we finished the last bit of the story. You can take carbon and fusing carbon make neon, and from that make sodium, and from that make magnesium, and I've outlined those chemical elements with rings on the table. And those stages will keep a star like the sun or a bigger one shining for about 600 years. Well, it would see us out. We don't live 600 years, but it's a relatively short lifetime, if that's true, for our sun. The neon can convert to oxygen. Here's the first mention of oxygen in the universe. Second stage here. That conversion for a star like the sun will last for about a year and keep the star shining for about a year. These time scales are shortening quite seriously. Silicon is built from oxygen. That stage will keep the star shining for about 6 months. And in one day, silicon converts to sulfur, which converts to argon, which converts to calcium, which converts to iron and nickel. And that'll keep the star shining for 1 day. Big deal. And you end up with iron and nickel, which is nifty stuff, but hard to get energy out of them, hard to sustain life if you've just got iron and nickel. So a late stage star, and this has to be a big star, 20, 30, 40 times the mass of the sun. If it's tidy, it may not be this tidy, will look something like this, with hydrogen on the outside, which is what we see, helium inside it, carbon inside that, neon, oxygen, silicon, and an iron core. That's not strictly to scale, that slide either, but it gives you an idea of what might be happening. So of the elements needed for human life, we've had hydrogen created, oxygen, carbon, calcium, iron, potassium, but They're all inside, well, most of them are inside this star, which ain't a good place to create life because it's far too hot. So how did we get the things like carbon, calcium, iron that are in our bodies? This is just for physics students in the audience and anybody else who's interested. What we've been talking about initially was hydrogen fusing to helium. Humankind has also managed to do fission, turning heavy elements like uranium into iron. Iron is the pits, it's the bottom of this graph. You cannot do anything with iron or it'll absorb energy. There's nothing free coming from iron. Having got our, maybe go back just a couple, having got our star in this sort of configuration, there's nothing it can do. And it seems the star explodes, making an end to that nice, tidy sequence of creations. This is a photograph of a small galaxy close to our galaxy. It's visible in the southern hemisphere. It was discovered by Magellan, and it's known as the Magellanic Cloud. There are actually two of them. This is the large Magellanic Cloud. And you can see a number of stars, particularly down bottom half and top right corner. Ignore the arrow for the moment. And let me just say, the arrow's not actually in the sky. It was added to the photograph afterwards. And there's a lot of nebulosity, shining nice red. This is hydrogen, remember? Pink nebulosity, hydrogen. Lots of hydrogen, lots of stars. The whole thing up top left is so much hot gas and so much hot stars that we can't see them separately. But there is this star that's picked out with an arrow. It looks very, very ordinary. There are lots like that in the slide. But watch that corner. That tiny little looking star has exploded. It was actually atypical, unusual in the sense that it was more massive, heavier than many stars. And heavier stars can get themselves in a situation where they do explode. And we'll be talking about that. This explosion is called a supernova. Nova is when a star comes bright, brighter than usual and visible, so it's new, so it's a nova. Supernova is when a star becomes extremely bright and visible, so it's a supernova. But they're very different processes. This one happened in 1987. It happened early in 1987, so it's got the letter A. It was the first one we saw. Now, one of these exploding stars is actually quite useful for our story. It gives 400 million tons of carbon, 240 of those of nitrogen, 60 of those of sulfur, 200 of those of radioactive nickel, and many other chemical elements in those kinds of quantities. The nickel is quite important in the sense that it's radioactive and it keeps the thing shining, the remains of the star, the supernova. It keeps it shining for probably several months, just depending on how far away the star is and how far you can see it. But here for the first time we've got carbon, for instance. And if we're getting that amount of carbon and nitrogen and sulfur, there's probably smaller amounts of other useful chemical elements as well. Every so often there is a panic about these exploding stars. If one went off close to the Earth, would it be dangerous? It might be. There's no risk that our sun will do this. Our sun is not a big enough, massive enough star. The nearest star that's likely to do it is Betelgeuse in Orion. That's the one on the top left. And there was a kerfuffle a year or two ago when Betelgeuse changed its brightness. He thought, oh, is it going to go off? It wasn't. It was a dust cloud that came across between us and it. Betelgeuse is still perfectly okay, thank you. But it will one day explode. However, it's more than 25 light years away, so if it does explode, the explosion is not dangerous to us on Earth. So that would be quite nifty, because these exploding stars provide some useful chemical elements, and if they're too far away, we'll never get hold of those chemical elements. So thank you, Betelgeuse, you're probably quite convenient. So an explosion like Betelgeuse will do one day, which is called a supernova, is a massive explosion. And it might leave just about one solar mass in the center, making one of these neutron stars that you might have heard of. But most of the material will go out at considerable velocity and can drift quite a long way and maybe land on some other planet somewhere. However, we've not yet got our full suite of chemical elements for life, let alone how they actually got here. They got here basically with patience. They got velocity from the explosion. They drifted. They drift to the vicinity of another star. That star's got gravity. Maybe that star is the sun. The gravity attracts the thing towards the solar system or whatever it is that's attracting them. And some of the stuff lands on planet Earth. Some of it lands on other planets. Some of it lands in the sun and basically gets a bit burnt up. But a lot of the chemical elements here on Earth were created in those explosions, were dispersed by the explosions, and traveled through space over millennia and got grabbed by the Earth's gravity. It's not a very ready supply of minerals, so we need to be a little bit careful about using what we've got. We can't turn on the tap and get a further supply. Unfortunately, at least we can't yet. But in terms of the chemical elements in us, some of them came from the Big Bang, certainly the hydrogen. We haven't got much helium in us, and there wasn't many other things created at the stage of the Big Bang. But the hydrogen in your bodies might date back to the Big Bang. Stars create a number of chemical elements. Some do it quietly, some do it with dramatic explosions. Either way, ultimately the material can get dispersed through star death and gradually fan out through space, and some of it gets attracted by the gravity of the sun and the planets and lands here on Earth. The ones that are in our bodies function that way. Some rather more special chemical elements, particularly things like gold, which is perhaps the one you're most familiar with, they, we think, are formed when two stars collide, which makes another kind of mega explosion, which will go far enough as to create gold, which then gets gradually dispersed out through the universe, and ultimately some of it ends up in a planet. But all these things need either the Big Bang or stars. And all the chemical elements in your body came either from the Big Bang or from stars. So you are made of star stuff, through and through. And all you've got to do now is shine academically. Thank you very much. Thank you for your interest.
Thank you very much for this quite impressive presentation. If any of you have questions for Professor Bell, it's time to shine too. Thank you very much. and pick one, Professor Bell.
Oh, I'm picking, right, okay.
Yes.
Since it's easier to describe, lady in the blue and white shirt.
I would like to ask you, what is your favorite star and why?
I rather like Betelgeuse in the constellation of Orion. It was one of the first stars that I learnt to identify. It's a star that's quite low temperature, so it looks red compared with other stars, and you can actually see that, or just about see it and convince yourself. So I can find it, which is quite good for somebody who doesn't use telescopes a lot, and it's of interest. It became rather more of interest a few years ago when there was a fear that maybe it was going to do something like explode. It turned out it wasn't the star, it was a cloud passing between us and the star. So, panic over. Yes?
So I have two questions. The first one is when you described when you talked about the knots forming and getting bigger and the temperature rises, can you explain why the temperature rises in those knots?
Okay, yes. So as the knot grows and collects more material, the pressure on the center material gets higher, density gets greater, and it's basically the overlying pressure that puts up the temperature in the middle. And it manages to put it up to some millions of degrees Kelvin, because that's when nuclear reactions start.
And my second question is, I would want to become an astrophysician one day, and what is do you have an advice?
Yes, yeah. You need to have a lot of physics if you're going to do astrophysics. We tend not to use the word astronomy in academia. We call it astrophysics because it involves a lot of physics. So good math, good physics are the important things. Got somebody right on the back row.
I would like to know what did you think when you saw for the first time a very recurrent signal on the sky?
When I saw the first pulsar pulsing, I thought, yeah. So I'm a grad student. With a supervisor who is quite senior and not always very sympathetic, shall we say. So you have to be very careful before you say, yeah, I found something. Even if you're right. I thought, this is really rather surprising. And I knew enough astrophysics to know that if something varies rapidly, it's small. And most stars are really very, very big. And they can't change on a period of 1 second. Well, we now know that there are some very compact stars that are only about 10 kilometers across, and they can do things quite fast. But we didn't know about them until this turned out to be these stars that were 10 kilometers across, or strictly 10 kilometers radius. So, yeah, it's what the heck is this kind of thing? And I think I didn't say anything till my supervisor. I had another look next day. I'm using what's called a transit instrument. It's fixed. You wait for the sky to go past your telescope. So you see something one day, and then you have to wait till the next day to see it again. So I think I waited for a second sighting. No, I know what I did. When I first recognized this funny signal, I went back through old records, and so it had been there before. So I knew there was something that was keeping its place amongst the stars. And it turns out to be something going blip, 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 which is far too fast for a star. And we had trouble sometimes with radar, airport radar. So your first thought is, this is airport radar. But it's keeping the 23-hour, 56-minute day. Doesn't come back 24 hours later, comes back 23 hours, 56 minutes later. In a week, that's 28 minutes, half an hour. Whose work schedule is like that? So it really has to be something astronomical. But yeah, my supervisor was very skeptical. I think if I'd been male, a man, he might have been less skeptical. But you know, with women, you never know. Okay, let's see. Questions on this side of the hall? Yes, sir.
Well, why did you pick?
Microphone coming at speed. Thank you.
Why did you
C'est normal. C'est juste pour le live, pour qu'ils entendent en live.
Why did you pick astrophysics as your subject?
Okay, so the question is, when did I pick astrophysics?
Yes.
Yeah. Going through high school, I was good at physics. And I thought I was probably going to be doing physics, but it's a vast subject, as you know, so what am I going to do? My father was very widely read, and he had a book home from the public library by, you may have heard the name, Fred Hoyle. Fred Hoyle wrote many books for the public, and this was one of them. And it looked interesting, so I picked it up. I was about age 12 at the time, probably. And Fred Hoyle is talking about the rotation of galaxies, because these big galaxies spin. And in physics classes at school, we're doing motion in a circle, centrifugal force, centripetal force, and it just matches the rotation of the galaxy. Like, ha! I could be an astronomer. So that was the root of it. Reading that book at about age 12 and suddenly realizing that physics at school at age 12 actually applies to the universe. Yes.
Thank you very much for your presentation. Just as a question, what do you think is the likelihood that those chemical elements have agglomerated in different stars than our sun and have produced life, either intelligent life or other kinds of life? And what is the likelihood of meeting that kind of life?
Yeah. There are an awful lot of stars and an awful lot of galaxies. The rough multiplication table that I use is 10 to the power 11 stars equals 1 galaxy. 10 to the power 11 galaxies equals 1 universe. Okay, it may not be accurate, but in terms of communicating with the public, it gives an idea of the scale. And our sun is a very average star. It's kind of in the middle of the distribution. So there must be an awful lot of sun-like stars in other galaxies and in our galaxy. I don't understand too well about why it has planets, how planets formed, but I didn't expect it to be anything very special. And now that we are studying exoplanets, planets around other stars, we know that planets are very common and that they come in a great variety of masses and radii and temperatures and things like that. The field of exoplanets is one of the fastest moving branches of astronomy at the moment. So I think the chances of there being life elsewhere in the universe are pretty good. I don't believe we are a special creation, for example. Whether those other people have managed their planet better than we have managed ours is another question. Microphone just coming, sir.
Thank you. What are the main subjects you worked on? I mean, beyond the pulsar.
Right. I got engaged to be married between discovering pulsars 2 and 3. I got married between submitting my PhD thesis and having the Viva exam. And I am no longer married, but for a good many years I was married. And then there is the problem of finding good jobs for 2 people in the same place. My husband worked in local government, and the way you get promotion in local government is to move to another locality and go up a rank. So every 5 or 6 years he would say, "It's time we moved." And he said, "There's a job going in this city. Is there any university anywhere near that city?" "Yes." "Does it have any astronomy?" "No." He doesn't apply to that job. But that's the way we worked it. And so he would get a job in a new city where there was a university that did some astronomy. and I have to write a begging letter to the head of department, seeing if they might have any money for a job for me. So I have worked in radio astronomy, infrared astronomy, millimeter wave astronomy, infrared astronomy, not visible, not ultraviolet, but also X and gamma ray, which is first of all a crazy career, but quite a lot of fun. And I'm always moving for the wrong reason and writing begging letters. So I've been a university technician and I've been a professor. Seen it all, done it all. Okay.
Thank you for your presentation. I had a question. The science wasn't and isn't an easy place for women.
Mm-hmm.
If you could today, would you accept a Nobel Prize if it would propose to you?
I don't think I will be offered a Nobel Prize, but yes, I do tend to, because there's quite a lot of publicity goes with these prizes, and that means people see that women are doing science and presumably doing it well if they have won a prize. Fraction of women in physics is getting better. In in my country, astronomy always has more women in physics, more women than physics. Higher fraction of astronomy is female. I don't know, is that the picture in other countries as well? Maybe, maybe not. But in general, it's getting much, much better. There are still problems about getting good jobs for two people in the one place. There are still issues about the women have to have the babies, the men can't. So the women's career gets disrupted by that. And how do we allow for that in the advancement, the promotion within a university? So there's still issues like that to sort out, but we're getting better at it. And more universities have creches and nurseries for at least the small children, which is good.
I just want to ask one question about our observatory. What do you think about it? Do you like it? And and what do you think about France also?
Yes, I think it's great, and I congratulate the people who've put a lot of work in, because it will be a lot of work, and it's work that's extra work over and above your job. So that's really fantastic. My experience is that observatories prove quite popular if you can open it to enable people from the city to come and see the night sky. It takes people's time, to open it, to explain, and to run the telescope. But I think it makes quite a big impact. And certainly in my country, and I think probably also in the USA at the moment, science is... So we need more things like observatories open for the public so they can see for themselves. Yeah.
Thank you, Jocelyn Bell, to come here. Just a little question for you. Can you tell us, during your fantastic career, who was the most surprising person you had to talk about your job?
I've met some very interesting people, and one of the advantages of being married to a man who moved is that I kept moving to different universities and meeting new people. But I think probably the most exciting time for me was I got to know a US astronomer, radio astronomer called Joe Taylor, who also worked in pulsars, who incidentally got a Nobel Prize along with his grad student, and took me to Stockholm as his guest. The Nobel Prize committee, what are they going to do? Will they interrupt the ceremony? King of Sweden, Queen of Sweden. We didn't, we behaved perfectly. But that was an interesting experience as well. Yeah. in Britain, certainly, our society is evolving. The roles of men and women are changing. Not fast enough for me, but that's okay. They are changing. I hope there isn't going to be a backlash. I can see that in the USA, the roles of women have gone back a bit since Trump became president. I hope we don't get a similar government in my country, or your country for that matter, but yeah.
Thank you very much for the presentation.
I don't think the microphone's working, so can you?
Okay, is it working?
I will translate for you.
Okay.
Thank you for your presentation. It's really interesting, and we had a lot of fun actually. And my question is more like after the first discover or proposals, and you realize it's an area no one had entered before. What's your first idea or first reaction about that? Do you have any idea like I would like to do as much as I wanted before any others to move attention to there, or still have a wide interesting to any other scientific field?
So I think you're asking around the discovery of pulsars?
Yes.
Yes.
After, what was your scope?
Yes, right. Okay. There were lots of interesting things just after the discovery. The press the newspapers particularly became interested. Television was not such a big thing then. And the newspaper interviews took a very standard format. There would be me and my thesis advisor. And they would ask the thesis advisor about the astrophysical significance of this discovery. And then they turned to me for the human interest. Maybe the women can see where this is going. What were my bust, waist, and hip measurements? How many boyfriends did I have? Was my hair brunette or blonde? No other colors were allowed. Really, absolutely, all the time, by all the press. It was shocking. And I think my thesis advisor was quite happy with that distribution of questions. Yeah. Microphone's coming from behind you.
Yes, thank you. So we talked about the life in the universe. Do you believe that aliens are little green men?
I created, sorry? Yeah. I created a bit of a problem because when I first identified this source, I labeled it LGM for little green men. And then the second one was LGM2 and so on. I didn't really believe it was little green men, but I knew it was something different from anything we knew about, and it needed a separate name. I wish I had thought a bit further ahead and, labeled it new source 1 and new source 2 and that kind of thing, which would have been much more boring, but might have actually advanced the science better amongst the public. You're getting a lot of exercise.
Thank you very much, Professor Bell, for your very interesting presentation. You talked about the Big Bang. Mm-hmm. Do you have an idea or favorite theory about what could have started the Big Bang? What could turn the light on?
I don't, to be honest, partly because I don't work in that area, but partly also I think it's a very difficult, probably impossible question to answer. For example, what we define as time started with the Big Bang. I'm not a good philosopher, so I'm unclear how much that's just a human definition and how significant it is. But if that marks the beginning, what on earth do you mean by before the Big Bang? That is a non-sense question.
Thank you.
think that's no, it hasn't quite silenced them.
Did you know how many stars have you studied?
Sorry, have I known for many years?
Did you know how many stars have you studied?
How many stars did you study?
How many stars did I study? Oh, yes. I think in my doctoral thesis I had about 200 quasars, and I was only surveying half the sky with equipment that now looks rather primitive. But yeah, but we found a lot of well, no, maybe I need to be more cautious. I found a number of things that were compact, strong radio sources that were compact, because it was the compactness that made them scintillate, which was the way I was picking them up. I think they nearly all turned out to be quasars in the end, but there would have been one or two maybe slightly curious stars or something like that, but nearly all quasars. So I think I increased the number of known quasars by a factor of 10 or something like that with my thesis work, if you believe that all my compact sources are quasars.
I have a question again. You said earlier that you had the awkward question when you discovered the pulsar. How do you respond to them?
Say that again a little bit more slowly.
Sorry. You said that you had the awkward question about your hair and
yeah,
things.
yes.
And how do you respond to them?
Yes, which is an interesting question. I respond to them, but minimally. So my hair was brown, my hair is now grey. Full stop. Next question, please. So don't give it too much attention, but don't be rude and refuse to answer, because newspapers have quite a lot of power, and it's not a good idea to make enemies of journalists. Up behind you.
Would you have any advices to get into radioastronomy?
Yes, do a physics degree. An awful lot of astrophysics is actually physics-based, so a physics degree will always be more use than an astrophysics degree, because if you don't get to do astrophysics, you've still got your physics degree and can get a good job somewhere else. So make sure you do lots of physics, I think is the important thing. I went to Glasgow University because they had an astronomy degree and I thought I was going to do it. But then I looked at the syllabus, and for the first year, it was all about the corrections you have to make to your telescope, little corrections, to make sure it points at the star you want it to point at. And I thought, that's boring. So I didn't do astronomy in the end.
What is the best advice you can say to us, to give us for young people? So, do you have one? Or
yes. Get a physics degree.
Generally, generally to do physics research.
The systems are different in different countries. In the USA, it's very common for students to join a research group for the summer vacation. In Britain, it is less common, and I don't actually know too much about the system in different countries. But if there is an option of a summer program, working with a research group, for instance, that's very good experience for a young person. May put them off, but you know, better sooner than later if that's what's going to happen.
If UPS in space discover a pulsar with his observatory, Is it okay to name it Jocelyn Bell pulsar?
You actually normally label them as PSR, then the right ascension, hours and minutes, and declination. So that's the normal procedure. And there is a catalogue of pulsars maintained, I think, in Australia now. It's probably at Swinburne. And that will be the notation they give it. Whatever you label you give it, it will be changed by the cataloguers. Cameraman up center top is.
If you had to study anything else but astrophysics, what it would have been?
Sorry, I'm not hearing very well.
If you had to study anything else but astrophysics, what it would have been?
Right, what would it be? I have enjoyed learning a number of languages. For instance, I worked for a while with Dutch astronomers, so learnt some Dutch. Their reaction was interesting. Now she'll understand our secret conversations. But I quite enjoy learning languages, so that was fun. For the physics, you also need very good mathematics. So you need tons of mathematics. And don't try and get away with less, because it won't work. So, those are the main things. But quite often, your university regulations dictate what you can do and you cannot do. You have some choice, but often not very much choice. And I could never have learnt Dutch as part of my degree. I think we're done.
It's my time. No further questions? No.
Good.
Well, thank you very much, Professor Bell, for answering all this question and for the presentation.
Thank you.
Very, very big thank you, and I think we can applause.
Good. Thank you, gentlemen. Thank you. Thank you. Thank you.
I will make the general remarks and the closing remarks in French to remercier principalement donc l'Université de nous avoir prêté cet amphithéâtre Concorde ce soir. Un grand merci aussi à Compute qui a fait la régie audio et vidéo pour ce soir. Et je vous remercie à tous d'être venus si nombreux et nombreux. Je ne vois pas ce que tu as dit. Ah oui, ben oui, j'y arrivais. Donc n'hésitez pas donc, à nous suivre sur nos réseaux et le 6 mai prochain, dans ce même amphithéâtre, nous recevrons Roland Lehoucq qui va lui nous parler de science-fiction et de la démesure dans la science-fiction qui peut être super intéressant aussi. Et comment ? Oui, en français. Je vous remercie à tous d'être venus. Encore une fois, merci. Thank you very much, Professor Bell, and see you.